in the first hour. Remember, ellipse is a general form and a circle is a special form. You were going to search for the answer, which is looking at the page on the textbook. So what is the answer? What should be the what's called eccentricity of an ellipse so that it's a circle? Şimdi egzantrik diye bir deyim vardır bilirsiniz. Ne için kullanırız egzantriği? Garip olan için. Güzel. Şimdi daire, circle is a perfect shape. If it's eccentric, it's not as perfect as you would imagine. So if the eccentricity is, it's a value between 0 and 1. If it's one end, it's a circle. If it's the other end, it's a line. So pull it all the way that it becomes so eccentric. So it's not even an ellipse, it's a line. So if the eccentricity is 0, then it's a circle. So an ellipse is a general form, as I said. A circle is a special shape, a special case of an ellipse. Now we have been studying the case of a circle because it's easier to handle, but later on, now we are going to see that we can use what we have seen and what we will identify as Kepler's third law to an ellipse, not just for the case of circular orbits. Now we have seen already the two laws of Kepler. What's left is what we already know, the third law. But in formal form, what Kepler stated is that a planet moving on an elliptical path around the sun sweeps equal area, the line connecting them, sweeps equal area in equal time in the first two laws. In the third law, he stated that the square of the period of its planetary orbit is proportional to the cube of what's called the semi-major axis. Now this is something new. Let's first identify what this is. Here is the ellipse. Here is the sun located at one of the two focal points. Here's the another one. Now this axis of the ellipse is called the major axis, and this one, the shorter one, is the minor axis. Half of it is what's called the semi-major axis. Now notice that if an ellipse has eccentricity of 0, its two focal points will overlap and it will be a circle. And then semi-major axis and semi-minor axis will be equal. So it's going to be just the radius. Now, with this reminder, here's the sun again. Let's formulate what Kepler stated in his third law. The square of the period of planetary orbit, this is the planet moving around the sun in an elliptical orbit, in a certain amount of time, for Earth that is 1 year, is proportional to the cube of the semi-major axis. Let's label it with A. So P square is proportional to A cubed. Remember, for a circle, radius is just the semi-major axis or semi-minor axis. Now, with our earlier arguments, we know that we can express this in full equation form, not just a proportionality that Kepler did, because he formulated, not even, I shouldn't say formulate, he came up with this statement empirically, just to explain long-lasting, long-period observations. But now, with our earlier knowledge, we can say that P square is 4 pi square over G, gravitational constant, times the mass of the sun times the cube of the length of semi-major axis. Now this is the full equation that we are going to be using. As I said just a while ago, we have derived this relationship in the first hour for a circle. But put the semi-major axis and you will see that it also works. Now here, this is the semi-major axis. This is not the radius. If eccentricity is 0, it's going to be the radius. So these are the 3 laws of Kepler that we are going to be playing with. But before that, let's take a look at something important. And let's determine the total energy of a planet. Now, for simplicity, let's make it on a circular orbit. I hope with the discussion at the end of first hour, you now understand why we assume that the orbit of the Earth is almost a circle. It's very similar to a circle. There is a slight eccentricity that makes it elliptical. That's why we feel the difference in winter and summer times. But the difference is so small, that means the orbit is elliptical, but very similar to a circle. So for simplicity, let's use the circular orbit approximation to determine the total energy of a planet. So Earth has certain amount of energy just by moving around the sun and just being in the vicinity of the sun. Earth is gravitationally bound to the sun. There's a potential that we are bound with. Otherwise, Earth would just fly away. Since Earth is not just taking off, that means there is the potential keeping us bound there. So the total energy will include potential energy, but let's remember, although we know very well how Earth-Sun system looks, here is the Sun, here is the Earth. And Earth, Sun are apart by, say, R. And there is the gravitational force that keeps us there. Now, you know this by heart. And it's radially inward, so we are attracted. The Earth is attracted. And we move in orbit on a circular orbit around the Sun. Therefore, there is the centripetal force. Its direction, as the name indicates, towards the center. It's center-seeking force. It's a constant speed, but the direction of it is changing constantly, all the time. So it's in the same direction. So we have this one already. We have seen this in the first hour. Now we can write the potential energy. Now, I'm not going to derive once again what the potential energy is. You know that force for a conservative force is minus du over dr. If it's one-dimensional, it's dx. If it's three-dimensional, dr. So to find the potential energy, you just have to integrate the force along the radial distance. Now, to keep Earth here, what you need to determine an integration to bring Earth from a distance at an infinity to a distance of r. So you know this from your earlier course content. So let's quickly go ahead and write that the potential energy that Earth feels is g m sun m Earth divided by r. This is the potential energy with which Earth is bound to the Sun-Earth system. The minus sign indicates that we are bound. If you somehow get this much of energy into your system, you will be free. Otherwise, you are bound. You can't go anywhere. So this is one element of the total energy. What is the other piece? The other piece is the kinetic energy. And kinetic energy is more friendly, mostly, because it's simply 1 over 2 mv squared. But this is the Earth. So it's the mass of Earth times a half times v squared, where v is its orbital speed. And that is constant because we consider that it's a circular orbit. What is this v? We already know this. It's a circular path. It takes 1 year to go around. So it's the circumference divided by the period. But let's not go in there because it's right here. You can solve this equation. ME's will cancel, and you will find that v squared, sorry that this is going to be capital R, v squared is, you can cancel 1 r's here too, will turn out to be g m sun over r. So I can plug this in. From here, v squared, since ME's will cancel, 1 r's will go away, there is only v squared here, and here we have g ms over r. It's v squared, it's v squared. So we don't have to take the square root. So kinetic energy is now 1/2 G ms me over R. Potential energy G ms me over R. Kinetic energy 1/2 G ms me over R. There's the minus sign, which is important. Now we have to find the total energy. Total energy is just the sum of the two. That is U plus K. And this is minus Gm over Gm EMS over R plus a half Gm SME over R. That will give you a total energy of minus 1/2 G ms me over R. Now let's take a look at the potential energy up here, kinetic energy right here, and the total energy. They look so much alike. Just the coefficients and the signs are different. Energy, total energy, is simply the opposite sign, kinetic energy. And it's also half of the potential energy. Total energy is just half of potential energy. Therefore, we can say that the total energy is half of potential energy or minus of its kinetic energy, which is known as the virial theorem. So, using virial theorem for a system that is moving on a circular path around the sun or central object, you can determine the total energy knowing the kinetic energy or potential energy. All you need to know is one of the three energies, then you know right away the other two. Otherwise, you just have to go through the whole thing. It's also easy to do. Any questions? So let's take a look at an example. We have seen quite a number of things, so let's see how we can make use of them. Now the question is, assuming that the orbit of the Earth, you know what we are going to assume after all, is a circle. Nothing surprising. We want to calculate the mass of the sun. So how can we weigh the sun? The simple way or simple-minded way is to send a scale and ask the sun to get on it. which is not very practical. Instead, we can use Kepler's third law. We know that for the Sun, Earth system that is now moving, assuming that it's on a circular path, circular orbit with a radius r, we know that g ms me over r squared, I'm not keeping the directions, we know by now that they are the same, is me v squared over r, and we know that v is the circumference of its circular path divided by the period of rotation. So you can obtain, after few steps, the Kepler's third law for a circular orbit. So I'm not going to redo it because we have done it already and you should do it yourself. So what you obtain is g ms, because me's will cancel, divided by r is 4r cubed 4 pi squared over p squared. Kepler's third law. From here, what we want to determine is the mass of the Sun. So we solve for it. That is 4 pi squared r cubed divided by g times p squared. And this is a hard-looking number, but it's easy to compute. R is the distance between the Earth and the Sun, which is 1.5 times 10 to 8 kilometers. That makes 10 to 11 meters. Remember, we use SI. P is the period, that is 1 year, but we have to convert this into seconds. So it's 365 times 400 seconds per day. It will be roughly equal to 3 times 10 to 7 seconds. So we can plug these in to determine roughly the mass of the Sun. 4 times pi squared is about 4 times 10 times r cubed is 6 times 10 to 33 divided by g, which is 6.7 times 10 to minus 11 times p squared, which is, let's say 10, why not, times 10 to 14. So you cancel things easily. So it's a little less than 4 because there is 6.7. So let's say it's 3, roughly, approximately. 10 to 33 minus 11 plus 14. So there is minus plus 3 down here. So it's about 10 to 3 times 10 to 30 unit is kilogram, because we do this in SI. Not far from the real number. The real number is 2 times 10 to 30 kilograms. So we can weigh the Sun with almost with a good accuracy by just putting in numbers and approximating that it's a circular path. So this is how we can apply Kepler's third law.
3 times 10 to the 33. It's even closer to 2 times 10 to the 1.5 cubed is around 3.
Oh, okay. 1.5 cube is okay, but that's even better. Okay, well, it's the exact number. So why don't we just assume that it's a circular pet? Okay, now let's take a look at something different. Now remember Kepler's third law for a circular orbit. It includes the radius cubed, period square, and some constants. So what is Kepler's third law? Now I'm asking you, after writing so many times, what is it once again, just to see if it's there. Kepler said p square, period square, is proportional to the cube of semi-major axis. So now we formulate it in a more understandable physical, logical manner, and we know now not just proportionality, we know that it's an equality. So G m sun over r cubed is 4 pi square over p square. Now let's rewrite this for something else. Now if it's a circular orbit, we can use the radius, but it's also valid for elliptical orbits, so let's put the semi-major axis there. And let's rewrite this for p square divided by a cubed. So I will just take p from here to there and g times ms down here. I'm just playing now that I have about 20 minutes, no questionnaire, so why don't we just play with it? So what this says is that on one side, right here, I have the period square over cube of the semi-major axis depends on a constant, 4 pi square, divided by another constant, and also divided by yet another constant, mass of the sun, which does not change. We are talking about the sun here at the center, and there are planets in elliptical orbits with orbital semi-major axis of A. So here is Mercury, here is Venus, here is Earth. Do you know what's next? That's the Mars. And there is a range of asteroids, and far, far out there, there is the Jupiter. This is Mars. And there's Saturn, Uranus, Neptune. Now, for any planet in our solar system, its period around the one revolution around the sun squared divided by its semi-major axis cube has to be the same. Because what you have here on the right-hand side is a constant for our solar system. Now, this is something you can verify. Please do it. Find those numbers and show yourself that p Mercury square over A Mercury square cubed is equal to 4 pi square over GMS, and that's equal to P square Venus over A cubed Venus, the semi-major axis of the orbit of Venus, and that's equal to, we have to write this 8 times, Earth A cubed Earth and also for Jupiter, why not, over A cubed Jupiter, and it's also valid for other 3 planets. Please do verify by finding out how long is a year on Mercury and how big the semi-major axis of Mercury. And do the same thing for Venus, you know already for Earth, and do for all, and you will see that they are almost the same. So that's yet another way that we can make use of Kepler's third law. Any questions? Now finally, we can, now that we know almost everything, we can define the gravitational acceleration. Let's consider that here is Earth, and you are here on Earth. Your mass is m, and the mass of Earth is capital M. And you are bound here, so you cannot just jump and go away. And you are pulled down. You all feel this force. That's why you are sitting. This force here is the gravitational attraction, Gm, little m over r squared. And using Newton's second law, it's simply m times a, the acceleration associated acting as a force on you. And for this particular case here on Earth, we call it m times g, where g is the gravitational acceleration. Now when you take the first and the last term here into account, again little m's would cancel, and you can determine that the gravitational acceleration here on Earth is just gm over r squared. And you can determine the value of it. It's not difficult to do. We know the universal gravitational acceleration, universal gravitational constant. The mass of the Earth, about 6 times 10 to 24 kilograms, and the radius square, radius is about 6,000 kilometers, so it's 6 times 10 to 10 to 6 meters squared. So it's 6 squared, 6, 6. They all cancel. 11, 24, 13 over 12, which is, not surprisingly, about 10 meters per second square. So what you have here is nothing but just the gravitational acceleration. If you were to determine the gravitational acceleration on the surface of Mars, you just replace this capital ME with the mass of Mars, and R with the radius of Mars. Then you will determine the gravitational acceleration that you would feel when you are on the surface of Mars. So this concludes our discussion on gravitational force, gravity, and Kepler problem. Next week, your instructor will be back and he will continue. But the 10 minutes will not pass unless we do a questionnaire. So take a piece of paper, write your name,